I wanted to welcome all of you and introduce Sidney Legget, who is one of our cross-disciplinary interns for this year's pilot program, Cross-Disciplinary Internship. Sid comes to us from the University of Winnipeg, and she's working with Professor Matthew Leybourne in the Kufer Lab at Queen's University as a part of the McDonald Institute. So thank you so much for being here with us today, Sidney. I turn the floor over to you and welcome your 10-minute presentation. I'll set a timer and then I'll start doing backflips when you've run out of time, okay? So a nice little virtual feature that I don't have in real life.
All right.
So, okay, well, welcome, Sid, and thanks so much for taking the time to share your research with us.
All right, so I guess as a quick start, before I start presenting, when you look at the screen, if you go up here, you'll kind of be able to do a full zoom in and look at it at a full screen. And then down here, you could just zoom in and still see the room. And then I will also do a quick introduction in Cree. So,
Tanse, Wápiskisiw Pinésiw Iskwéw natisnakaso. Nina anau askihe kan ak histasoin peak. Kinanan skomitten anis anawin oma. Ikosi maka kitwam ka wapamitten.
So hi there, my name is Sidney Legget, and I'm currently in Treaty 1, the territory of Anishinaabe Nation, Dakota Nakota Nation, Cree Nation, and also the homeland of the Red River Métis. And I want to say thank you for being here and listening to my talk. So I am a fourth-year statistics student specializing in data science from the University of Winnipeg, and I am minoring in computer science. So this summer, through the cross-disciplinary internship, I got to work with Dr. Matthew Leybourne, who is a part of the McDonald Institute and Queen's University and is a geologist. So while working with Leybourne this summer, I came in with some skills in scientific and manuscript writing, but I got the chance to learn a lot more skills and good practices than I could have imagined taking this research position. I also got to put my own skills of analysis and programming towards a brand new field for me. So learning about geology, chemistry, and physics this summer opened my eyes to how many fields are impacted by learning more and having skills in these sciences. And I'm grateful for getting the chance to experience that this summer. So now I'll begin my poster presentation if you want to look at the screen. So our research project is called Lowering Detection Limits of Rare Earth Elements in Terrestrial and Marine Waters Without Pretreatment using the triple quadruple ICP-MS analysis. So as an introduction, we will start with determining rare earths. Rare earth element analysis comes with significant challenges. For terrestrial waters, rare earths are typically found at low concentrations, commonly near the 1 parts per trillion level. These low concentrations can be impractical for most methods where the rare earths are below instrument detection limits. In marine waters, there is a need to dilute the samples because of salinity. These high salinities result in signal suppression in an ICP-MS plasma. In both terrestrial and marine waters, the formation of oxides of the light rare earths and barium on the middle and heavy rare earths, in particular europium, poses a challenge when determining the rare earths. Next, we discuss the transition of using traditional methods to the new and recent advances we are using with our research. So in this section, previous methods have included pre-concentration via chromatography, precipitation with hydroxides, and evaporation and analysis by quadruple ICP-MS or high-resolution ICP-MS. The primary issue with high-resolution ICP-MS is to achieve inference-free analysis of the rare earths. The increased resolution results in a loss of sensitive higher detection limits, and the high-resolution ICP-MS is slower. So recent advances in quadruple ICP-MS provide an alternative approach, termed in-situ chemical chromatography, using a combination of two analytical quadruples and a reaction cell. Currently, there are two manufacturers, Allegiant and Thermo Fisher Scientific. We present such an approach to the analysis of rare earths in ground and surface waters from the high Andes, and then also marine waters from an estuary, utilizing the ICAP triple quadruple from Thermo Fisher Scientific. Next, we will talk about some of the methods that I consider. The method detection limit is the lowest level REE that can be detected in a sample matrix using our method analysis, considering the steps we took to prepare our samples. Samples were taken from the ground and surface and estuary waters, and then background equivalent concentrations are in the 10th to 100th of a parts per trillion. Now to discuss the results. First, we will look at the results from the ground and surface waters. The ground and surface waters have levels of detection generally in the extremely low parts per trillion range. The detection limit ranged from the lightest rare earth elements, such as praseodymium and cerium, having concentration limits near or lower than single parts per trillion, and some of the heavier rare earths, such as ludium, are also at or near 1 part per trillion. In these waters, one of the relatively larger but still very low elements in the parts per billion range was europium. This was the only rare earth to have a level of detection at 0.001 parts per billion. When another trial to see the detection for europium was done, it was also able to get in the low part per trillion range. The standard concentration set for most of the rare earth samples in the ground and surface waters was about 0.01 to 1 parts per billion, with concentration RSDs from about 0.9 to 12.9%, and concentration averages from 0.01 to 1 parts per billion. Then in the estuary waters, they have levels of detection around 0.001 or 0.002 parts per billion for the rare earths such as lampium, samarium, europium, and ytterbarium. All other rare earths, including europium in another trial, had levels of detection lower than 1 parts per trillion. Here the samples also had standard concentrations in the 0.01 to 1 parts per billion range. The concentration average also was similar to that of the surface and ground waters at 0.01 and to 1.0 parts per billion. The concentration RSDs estuary water samples range from 0.4 to 10%. And here in the middle of the poster, you can see calibrations of detection limits for cerium in both waters, and then under that, the normalized rare earth patterns for both waters. Now, what does this mean? Well, in the past, there have been many studies on determining rare earth elements with ICP-MS methods. These studies have reached detection limits around 300 parts per trillion to some limits in the smaller parts per trillion range. And then they have levels of detection higher, such as in the low parts per million range. And then we have some key aspects of the triple quad. Since it is made for routine analysis and to achieve minimal contamination to help ensure consistent data, it comes with enclosed sample handling to avoid atmospheric contamination. Cold plasma operation in the machine improves detection limits at concentrations lower than parts per trillion levels. This technology combined removes argon-based inferences while using the cold plasma enables the ICP to run at a lower power. And then this suppresses the ionization of argon and carbon, which removes polyatomic species that could have interfered with target analyte ions. This system allows a range of ICP-MS, such as cold plasma, kinetic energy discrimination, and triple quadruple. Performance you need from the machine, depending on the element being analyzed, can be altered and the modes can be changed. So when using this new machine, we had samples from the fresh and seawater, and we were able to reach detection limits of 0.001 parts per billion or lower from the rare earths such as lanthanum, and the highest were between 0.002 parts per billion in ytterbium. Achieving this limits this low without pre-concentration methods beforehand means even samples with extremely low concentrations of rare earths, such as that below 0.001 parts per billion, can be determined without requiring a larger sample. The triple quadruple being sensitive enough to reach these levels of detection enables rare earths to be determined more effectively and efficiently, since it'll be avoiding mass inferences, contaminations, and more than that came with the previous methods. Now for the future, these capabilities from triple quad have levels of detection capable of determining rare earths from the samples with low concentrations will enable us to determine quicker and more reliable. Being able to determine the rare earths is important since the use of them in modern industrial forms has been increasing, and the accurate determination is needed for monitoring the changes in the environment and ongoing studies. So what does this mean for astroparticle physics? With the triple quad ICP-MS being proved effective for our study, this equipment can also benefit studies done for the field of astroparticle physics. This can be a useful tool because of ultratrace detection limits, also needed to be pushed in the astroparticle physics world. It will be especially helpful for ultratrace detection of background contamination in this field. I'd like to thank the Institute, Queen's University, and of course, Matthew Leybourne for giving me the opportunity to be a part of this research and the community. Ekosi maka kitwam ka wapamen. Thank you.
Well done, Sid. Fantastic. Everyone, click your F4 function and give her a round of applause. There you go. Thank you so much.